Welcome to my channel. So today's topic of discussion is water and the ability to harvest water from your roof and how to use it or what would be appropriate for its use. With that being said, I'm speaking specifically for America and the areas of America that I'm talking about are the continental United States. We could talk about Alaska and we can talk about Hawaii as a separate entity because their climates are so dramatically different from the continental United States. In other words, there's 48 other states that this would affect better. So, depending on the climate, catching roof water could be a benefit or it could be a hazard. It would be a benefit in drier climates. It would be a hazard in snow-based climates or really cold areas where they get snow dams on the rooftops. The rain gutters in areas that get feet of snow per year, the rain gutters may just get ripped off. So having rain gutters may be of no benefit. In that case, there could be a diversion, a way to divert the water when it's liquid without trapping the water as heavy ice when it freezes. And that's a discussion for another day. Currently, this discussion has to do with issues concerning water catchment from a rooftop. In America, and I'm specifically speaking about the United States of America, not Central America or South America, just North America, United States. We use a variety of rooftop materials. The general materials we use are concrete tiles, terracotta tiles, slate tiles, wood tiles, metal roofing materials, and composite materials. And the composite materials are made of a tar, sand, gravel base with a matrix that holds it all together. The majority, not every roof, but the majority of roofs currently being built are composite materials. That means they have a tar base, and that means they have a heavy petroleum distillate that when we catch water off of a roof surface, we have to be aware of. So to give you an idea of how much catchment area we have in America, I'm going to give you some rough estimates of volume. For the first volume metric, you have to understand a basic number. 1 square mile of hard surface runoff with 1/16 of an inch of rainfall running over the total surface area per event is 1.086 million gallons of water. That's a lot of surface area and that's a lot of water, and we funnel it straight to the ocean, or the lowest point that we can get away from us, to rivers, streams, and oceans. We funnel that water away from towns and cities for flood reasons. With that being said, that's every square mile of hard surface runoff. So if we were just to talk about the roof area of houses, many houses are in the 2,000 square foot range. Not all, and I'm not discussing commercial buildings or industrial buildings. I'm just talking about residential homes. So if the footprint is 2,000 square feet, which is a fairly common size, we can multiply, we can take the population of America, which exceeds 333 million people, and there's roughly 4 people to a house, roughly, give or take, you know. These are just rough ideas. So you can take 333 million divided by 4, and that's how many theoretical houses are in America. Unfortunately, it does add in Alaska and Hawaii, but Hawaii's population is very small. Alaska's population is very small. We're not discounting them, but we're not really counting them in this equation. But these are just rough numbers anyways. So you take 333 million, you divide it by 4. That's the rough number of houses that you have. Then you multiply that by 2,000 square feet. That's the surface area that we're discussing. And then whatever that surface area is, you break that down into square miles, okay? Because that's square feet, and it turns into square miles. And once it's at the square mile mark, every 16th of an inch of rain is 1.086 million gallons. In Monterey, California, where I'm at, we roughly get 21 inches of rain a year. Well, that equates to about 364 million gallons of water a year per square mile. I don't know what that translates into in acre feet, since we calculate in acre feet, not square volume. We calculate in surface area in acre feet. I don't know what that is. But 364 million gallons of water per year times how many miles of surface area running off of roofs. So that's a lot of water. There's some mathematician out there that's crying in his beer right now because he's probably got a better equation than I do. Leave it in the comments below. Don't argue with me about it. I have the ability to be wrong. I sent the math before my mathematician, and my mathematician said my math was accurate. I've been known to be wrong before. So, when it comes down to a single house, this could be thousands of gallons a year. And most of it's going to be runoff, because we're not going to try and capture all the water off a roof. But we're going to try and capture some. So with roof catchment, we have to decide what the usage of said water is going to be. Whether it's for watering plants, or washing cars, or helping, do laundry or something, or whether it's for showering, or whether it's for drinking purposes. In most municipalities, you're not going to get to the drinking level unless you put in a lot of effort, time, and money into technology. And we're going to get to that in a minute. So when the rain comes, water in the sky and condensed clouds is considered distilled. But it can have any contaminant that's in the air, in the water. Sulfuric acid, salt, aluminum. It can have any contaminant that's airborne. If it's in the cloud and it condenses around that particle, it's going to take that particle and drop it out as a raindrop or an ice nuclei if it gets heavy enough and it's cold enough. And then as it falls towards the ground, it'll probably turn back to water. If it doesn't, it lands as snow or hail or sleet. But when it gets to the roof level, it may be contaminated already. The water may be. Then it touches the roof surface, and whatever is contaminated on top of the roof surface, it picks up. And then it goes into the gutter, and whatever is contaminated in the gutter, it picks up. And then it goes down the downspout. Whatever is contaminated in the downspout, it picks up, and it goes into the cistern. So to start avoiding that problem set of contamination, We do screens on our gutters to get most of the organic material to slide off. When we get to the downspout has a diverter for debris, and then water passes the diverter and the debris falls off to the side. When the water gets down to the bottom of the downspout, there's a first flush diverter. So if any contaminates, bugs, feces, oil, it gets picked up in the first diverter. After the diverter, it gets picked up in the first flush system, fills up the first flush system. The first flush system tips over and dumps that material out, and then closes again. While the rain is still falling, the first flush system is closed off, and water is diverted into your cistern. Now, that does not mean that your water in your cistern is uncontaminated. Viruses and bacteria and oils and chemicals are extremely small. And none of the objects that I just told you about, whether they're screens, mesh, filters, diverters, none of that gets rid of those contaminants. It just takes the vast majority of it out of the way, gets it moved away from the cistern to not contaminate the cistern very much. So some options in the first cistern to reduce contamination of that water. We can fill the cistern halfway to 2/3 with sand. And I think silica sand purchased is a very good source of material. Silica sand is the same stuff we use for glass. And it's a very clean material. And we can heat it and burn off any organics that are in it through an oven. So we can reduce cross-contamination out of our sand into the cistern. So the cistern would have a tube that goes down to the bottom and allows water to burble up through the sand. And at that point, at that stage, the sand acts as a sedimentary filter. As it acts as a filter, it's going to capture the large majority of the large particles of organic materials. When it gets above the sand layer, there'll be a pipe an inch or two above that allows water to siphon off into the second cistern. The second cistern can have sand also, or it can be clear, not have any sand. And at this point, that water is still not considered clean. It has the vast majority of large particles removed, but it does not take out fine particles. The space between grains of sand can be as big as 1/16 of an inch. And viruses and bacteria, mold and pollen and oils and things can be less than, or they can be not less than, they can be between 1 and 5 microns. So 1/16 of an inch is huge compared to 1 to 5 microns. So viruses and bacteria can still pass. When the second cistern is full, the water will settle out any debris to the bottom, any heavy particles to the bottom that are still floating through the system. Some organics may still float through, maybe layered at the top. Carbon has a tendency to do that. A lot of things are made of carbon, so just there may be some material settling at the bottom as a scum layer on the bottom, and then some fine organics may still float on the top. At that point, the water is still not clean, but we can filter the top water off into a third cistern. Now, at this point, the third cistern still isn't clean. Okay, the water is still not considered clean. You don't need the third cistern from this stage, but it would be more ideal. When the third cistern, the third tank fills up with water, we can then take that water and we can pressurize it and put it through a filtration system. The first filtration system could be standard house filters, but it's not going to get anything below 5 microns down. The second stage of filtration should go to reverse osmosis. Reverse osmosis gets everything underneath 1 micron out, so no organics can pass. In other words, basically just water passes. And that is considered safe for utilization. So at that point, but we have to recognize that reverse osmosis filters can be expensive for the homeowner. It can be $60 a set of 3 filters, and depending on the volume of water passing, because it's all based on volumes of water and contamination of the water in the filter, not determined by time. That could be every 2 to 6 months, depending on the amount of water going through that filter set. So just think, $60 every 2 months times 12 is your rough number if you're using a lot of water. $60 every 3 to 6 months is if you're not using a lot of water. You can do the math. It's not too complicated. Once you've gotten to reverse osmosis, you've taken almost all the particle mass out. Now, what is missed by reverse osmosis that has to be addressed is sometimes there's oils that pass, there's chemicals, things that are not particulate matter. The companies that are concerned about this is the fuel industry, which pumps oil out of the ground and distills it. The distillation factories, which distill the oils into fuels. The storage of said fuels in storage locations, as well as distribution points, gas stations and things of that nature. And then also we have the military and our scientific community that deals in chemicals that can attach themselves to water and bond fairly permanently. We want to make sure that we do not contaminate our aquifers. So in this being said, we also don't want to contaminate our cisterns at our house. So some ways to work around those chemicals and to get those chemicals out, and I by no means am advocating any one particular thing over another. This is just a discussion, and concerns of past this should be taken up with your local council, your local plumbers council, stuff like that. Certain chemicals bind themselves to water very, very easily and then are very hard to remove. We found that out because certain rocket fuels bind to water and they're extremely difficult to separate. Reverse osmosis isn't enough. So I'm going to start discussing how to get around that problem. And there's a lot of information on this out there, and this is for research, so if you need to do more research, please do. Don't take my word as the final word on this subject. That would be ridiculous. So the first thing I want to discuss is UV light. Ultraviolet light is very good at breaking down organic material, and ultraviolet light has the ability to help disassociate certain chemicals in water, but they would reassociate fairly quickly if they're not volatilized off. And UV light does not do that. There's no way to volatilize off the chemicals. So the chemicals may rebond, but any organic material, any virus or bacteria would probably be destroyed by the ultraviolet radiation being passed through the water. So that does not get rid of any further contamination, but there shouldn't be any contamination after reverse osmosis. So now we're getting down to the chemical level. The next thing that can be done, and this is more elaborate and slightly more expensive and should be considered well before being done, is to create a distillation system. Distillation volatilizes the water to vapor and then recondenses it, leaving behind solid mass, any particulate matter, anything that would turn into a salt crystal. And then the salt crystals can be scraped away and removed out of the system. And that can be anything from gold to aluminum to sodium to any of the heavy metals, anything to be left behind and not volatilize off when the water is turned to vapor or steam. In the process of water turning to vapor or steam, it has to be condensed. So there's a condenser coil that's above and usually at 45-degree angle or slightly less to the distillation unit. That loop is a minimum of 3 loops, usually of glass in scientific cases, but it could be aluminum or other materials that would drop heat very rapidly. It can have fins on it if you want, and that would drop heat even faster. It can be shaded. And when the water condenses and turns back into a liquid, you have 99.99% pure water. There's almost no possibility of contamination. So you've gone from 99.99% filtration from reverse osmosis and 99.99% filtration through distillation. The next phase is a little bit more elaborate, a little bit more expensive, and I recommend thinking about this long and hard before any money is put into said system. In the event that a chemical is still bonded to the water molecule and it cannot be released through distillation or UV radiation or mechanical filtration, then we go to electrolysis. Now, electrolysis, you put in an anode, you put in a cathode. They are a certain distance apart from each other. There's a current that passes between them. They break apart the oxygen and the hydrogen. Oxygen goes in one side, hydrogen goes in the other. You take off the hydrogen and the oxygen, you take them away, you put them back together, and you have pure H2O. In the process of that happening, the chemical that you don't want is volatilized off. If it can be figured out, it can be siphoned off, and you won't get it in the process of recombining hydrogen and oxygen. That is more elaborate, more expensive, because you need some form of electrical voltage. You need it to be in DC. You need it to be consistent current and consistent voltage, and you need a power source, whether it's photovoltaics with a battery pack or whether it's direct plug into the electrical grid. It still has to be there. In the process of electrolysis being implemented, you're going to have 99.99% pure water on the other side. The potential for contamination basically drops to 0 because you have 99.99% removal of contamination through filtration. You have 99.99% removal of contamination through distillation, and you have 99.99% removal of contamination through electrolysis and splitting of the molecule. And there is no other process that I know of that can be done to separate molecules from each other. Fractional distillation and distillation are basically the same. Same effects, same reasoning. The difference with fractional distillation and distillation, as I just said, is that fractional distillation uses a very large tube, and they heat things like oil and waste crude, and at atmospheric heights, different chemicals stabilize out at different densities. The heaviest density molecules are on the bottom, like lead, zinc, cadmium, heavy metals, and then the heavier gases like argon and oxygen, CO2 volatilize next, and they're in layers. And in the atmosphere, they condense out at certain heights. And we know those perfectly. We've been doing that for a while now. And then they take tubes and they siphon off the gases, and they use a condensing coil, and they condense it back into a liquid or a gas that's usable, and then they compress it. And then it gets shipped somewhere, like a factory. And they compress it further, refine it further, and off to use it goes into a bottle, a cylinder, or a vessel. Fractional distillation is not reasonable for a home system because fractional distillation units have to use atmospheric height to separate out materials. And they do it in bulk. Fractional distillation is done in thousands of gallons to get enough volume to actually be economically viable. But it works. So now you have a product on the backside of decontamination, and the likelihood of a home having all those processes is really, really tiny. You have to be really rich to have all those processes. So when you start removing those processes, you increase your chances of having a biological organism come through or a chemical contaminant come through. To render biological organisms inert, we terminate them by changing the pH balance. And the way we do that is we add chlorine. Chlorine is a toxic chemical. Its pH is somewhere between 12 and 13. I think it's in the 12 spectrum. That's very alkaline, by the way. Most life happens around 6.5 pH to 7 pH, somewhere in there. And nothing that we know of can withstand a pH shift of more than half of 1 part of pH. So if an organism's living at 6.5 pH and it shifts to 7, it's at its most extreme survival condition. It's 7. If it's at 6.5 and it's happy and it shifts down to 6, it's at its most extreme in shift. Anything past that and it terminates in either direction. There are very few organisms that can withstand a pH shift shock. And that's why we use chlorine, because the shift shock of pH is so hard. It's so hard from slightly acidic to alkaline that the organism's homeostasis fails and dumps its dioribonucleic acid out, trying to neutralize a base, and it, as it fails and does this, it dies. Now the chemical contaminant inside the organism is theoretically still there, but the organism is no longer reproducing and cannot create more contaminant or ingest the contaminant and concentrate the contaminant. And the solution to almost all pollution is dilution. You dilute any chemical far enough away from itself, from any other chemical, the dilution factor becomes the neutralizing factor to a point where, 1 part to 1 part would be toxic, but 1 part to 1 billion parts, probably not toxic. The likelihood of having a high enough concentration to be affected by 1 in a billion, there's a few chemicals out there that are dangerous like that, like phosgene. We don't want to talk about that. There's certain dioxins that are very toxic at parts per billion. Those are not to be discussed. The point of the matter is that 1 part per billion, the toxicity is extremely low versus 1 part to 1 part. That's just a reference point. So, in the process of cleaning up water for usage, we have to recognize what was potentially in the water, the pH of the water when it came out of the sky, what was on the roof, what was potentially on the roof, how to separate those materials out from the water to get it to a point where it's usable to water a lawn or take a bath or drink. And I'm not, again, making official recommendations. This is for study and training purposes. You want to look this information up, go find out what you know, or if you know something, you need to add it into the comments and bring it forth to the community. So when water falls out of the sky, there's a lot of CO2 in the atmosphere. And as water falls out of the sky, it intercepts the CO2 and makes mild carbolic acid. Very weak, extremely weak carbolic acid. And that falls through the trees and picks up nutrients and minerals from the trees and bird poop and rat poop and insect feces and stuff. And all of that can hit your roof. And it's considered a contaminant. That goes into the gutter, washes into your cistern, and you have a contamination problem. This is why we filter materials. This is why we put it through sand filters, and then we put it through sediment traps, and then we put it through home filters, and then we put it through reverse osmosis, and then we put it through UV radiation, and then we put it through possible distillation and possible electrolysis. Before water is drinkable, in the event that there's a contaminant still after all those processes, which is like nigh impossible, we would chlorinate it to kill anything that's left. But you get anything that's left after reverse osmosis, and it's amazing. You get anything else after UV radiation, amazing. You get anything else after distillation, amazing. I mean, we're talking, there's a mathematician out there that can calculate all this. I'm not going to do it for you right now. I'm not going to waste my time. But the potential for getting sick from reverse osmosis water, distilled water, UV treated water, and electrolysis treated water is finite. It's a number that's so small it boggles your mind. But many people don't have the dollars to effort to spend to do that. So a lot of people go to the sand trap and then they stop. Well, the sand trap's enough if you want to water your lawn, or you want to wash your house down, or you want to wash your car. There's nothing wrong with that. You're going to get most of the biologics out. You can wash your car and your house and water your lawn and your garden and do whatever you want with that water, as long as you don't drink it. You know, wash your hands inside after you use that water, because who knows what the biologics are in it. If you can get the water through a filtration system, even a baseline filtration system, at least you get the sediment out. Okay? Sediment filters do not filter out biological hazards. But it won't make your car dirtier when you wash it, or your house dirtier when you wash it. You need to get the TDS, the total dissolved solids, out. And that's what filters start doing. They get the TDS out. They stop allowing minerals to pass. Reverse osmosis works really well to stop minerals from passing and biologics from passing. And if you can pressurize that water at some point, then you can really wash a car or your house, or feed your lawn some water. If you need that water to be drinkable, you need to test it. And there's a lot of colleges out there that have testing systems to train their college students for what's in water. If you get a microscope, you can look in the water and see if there's, in the drops of water, and see if there's protozoa or things growing in that water. You can get a microscope up to 1,000 zoom pretty cheaply, like we're talking under $1,000. And you can study this stuff all you want. You can go take courses on it. There's nothing wrong with that. You can check the pH balance easily enough too, because to have drinkable water, the pH has to be fairly neutral, because water's baseline is 7. Okay, now if the pH in your water is 4.5, you're not drinking that, because that's contaminated with probably sulfuric acid, and so pH has to be adjusted also. We have a lot of sulfur in our air from industrial contamination from America all the way around the globe to China and Japan, and it all circulates back around in the northern hemisphere. So while we're talking about chemicals, there have been studies that have tested snowfall for pH balance and found snowfall that was down in the like high 2s. And that's like battery acid. That's like sulfuric acid falling from the sky. That's not good. When we talk about heavy metals become soluble at pH 4.5. And that is toxic to everything. Heavy metals being uptaken by plants or humans is toxic. If you want to learn about heavy metal toxicity, go look at Flint, Michigan, and how they changed their water supply and allowed a contaminated lead-based water supply to go to the city of Flint, Michigan, and be used by the residents. When the authorities knew that the pH had fallen below 4.5 and that lead and other heavy metals could become soluble, and humans could uptake that, but because it was cheaper to do that instead of maintaining their filtration system, they chose money over humans, and Flint, Michigan paid the price. And that was a big news story, and it should still be a big news story. The people that are in charge, and that were in charge at the time of Flint, Michigan, should be held accountable for their actions, because that was not that long ago. So, not trying to get into a political aspect, just giving you a representation of when metals become soluble and become hazardous. So, how do you adjust the pH inside your tanks? Well, because you don't want the pH to be 4.5, you can float limestone in your first tank with the sand. If you don't have limestone, which is a calcium-based material, you can use seashells, which are a calcium-based material, and they'll help neutralize the acidity of that water. And this is very easily testable, because you take the lid off and you look at your bag of shells, and if it hasn't decayed, then your water is probably okay. If you look at the limestone and the limestone hasn't decayed, then your water is probably okay. When the shells start deteriorating and going away, they're neutralizing the acidity of the water, and you can add more shells. You can add more seashells. And, of course, you want cleaned seashells. You don't want dirty seashells from the seashore. Say that 10 times fast. Because Sally ain't here selling you seashells at the seashore. Okay, so the point that I'm trying to make is that you have the ability to reduce your, or to not reduce, to raise the pH in the water by neutralizing any acidity coming off the roof. In that being done, the water will drop out of solution any heavy metals, and they will not be uptaken in the next cycle. They'll drop out. They'll fall out of suspension, I believe is the term that we want to use. But again, that gets removed also by filtration. So anything that did pass, that's why we filter the waters, because we don't want heavy metals. We don't want cadmium, iron, lead, zinc, molybdenum, any basically heavy metals, any metals at all. We want to minimize any metals going through the water system. Chromium, copper, doesn't matter. We want to minimize it. So once we balance the pH, we filtered the water, we buffered the acidity, and it would be odd to have water be alkaline off the roof. It'd be extremely odd. So it's unlikely that you'll need to add a acidic additive to your water base to neutralize it. It's very unlikely for water to be 8 or 9 on the pH scale or above. It's extremely unlikely, unless you have a contaminant on the roof that would cause that to happen. But falling from the sky, again, it starts off as carbolic acid in water. Probably has sulfuric acid from industrial processes. Probably has some aluminum in it from industry and space vessels falling out of the sky. And we want to remove the acids and neutralize those chemicals and toxins. And the way we do that is we buffer the pH. And we get the material to settle out of suspension. So those are some ideas on water quality. And the EPA has a lot of information on this. You can look at the EPA's website and find basically free information all day long on water quality and what needs to be done for water quality to be consumable. And the EPA disagrees with the water boards of the cities, by the way. The EPA clearly states fluoride is a toxin and should not be added to the water source. It should be removed because it's toxic to fish and invertebrates and humans. The EPA also states that chlorine is a toxin. Okay, so the Environmental Protection Agency has to work pretty closely with the water resource boards of any council of any city, trying to remind them you're adding toxins. You have to minimize your toxins to not harm the public while you're protecting the public from other toxins. And we have to be very, very careful about that because that's a really, really political hot point. But ingestion of fluoride is a problem. You don't want to ingest fluoride if you can avoid it. You also don't want to ingest chlorine if you can avoid it. So homes should have filters on them, and it should remove fluoride and chlorine and ammonium chloride out of the water set before a person drinks it or even showers with it. That's something that has to be considered by the homeowner. But if you do a little bit of research, and I have done quite a bit of research on this, fluoride is a topical mineral that puts a layer on teeth when it's topically applied with a brush and then left for a specific amount of time and then rinsed off. If you ever read the package on a package of toothpaste, it specifically requires you not to swallow and to rinse your mouth thoroughly and never ingest the material. Why? Because it's a toxin. One of the things people don't know about is that rat poison, the stuff they use to kill rats, which kills the predators that eat the rats that are dying from the poison and causes the rats to explode out of control. The poison that they use is a fluoride base. And to be very clear about this, fluoride does an interesting thing when too much of it is ingested. The rat ingests this material and then hemorrhages internally and dies, leaving a trail of liquid bleeding rat behind it. I can tell you, I've been under a lot of houses that have set bait traps, and I've found the remnants of rats at the end of this blood trail. And that is not something that I like seeing, because I know that if the homeowner's dog gets a hold of that rat and eats that rat, the dog has the same problem and dies. And then the homeowner goes to the hospital and goes, oh my God, the vet, and goes, oh my God, my dog is throwing up and defecating blood. What do we do? And the vets go, nothing. You could put the dog down. The dog's been poisoned and can't survive it. It's a tragedy. I knew a gentleman that I cared for very much, and he refused to get rid of his rat traps, and he went through 4 different dogs while I knew him. Each dog cost $5,000, not including training, feeding, housing, puppy classes, and none of those dogs lasted more than 3 years before they got a poisoned rat and died. So fluoride is a poison in a high enough concentration. It's a toxin in a low concentration, and it serves no purpose inside of drinking water for your teeth. Since we use a fluoride-based toothpaste, which is where we get the benefit of calcification on top of the teeth, preventing some level of cavities on the surface of the teeth while we brush. And then we have to rinse our mouths really clearly and cleanly. Do you need to know more about that? Go check it out. Go check out fluoride. Find out what's in rat poison. Go learn about it. I'm sure there's some pest control agencies that are like, no, that's not true. We use a different thing now. Great. Put it in the comments below. Tell me why, if you're not using fluoride, why you're not using fluoride as a terminator for rats and mice. Want to know, because that's what it used to be. It's possible it's changed. But again, any poison, any biocide that gets into a food supply or a water supply has to be removed before it can be, the food supply or water supply can be used. Enough of that. If you have anything interesting to say, put it in the comments below. If you like this kind of content, you want to see more of it, give me a thumbs up. If you really like this content and you want to see more of it directly, subscribe. If you really, really like this content and you really, really think it's interesting and you really want to share this interest with others, share this video with a friend. The way we get the information out there is by communication, and I'm helping to communicate with you. I'd like you to help communicate with others, and we can work out solutions to problems that have been long-standing and yet can be solved. We are Homo sapiens, and they are highly intelligent. Have a great day.